Alright, so we're quickly going to talk about some proofs with similar triangles. And again, our definition of similar is roughly the same shape, different size. More concretely, it means that our sides are in proportion, so they have a ratio, like 1/2 or 3:1, that make them together, and that the angles are congruent. So we're going to look at some specific cases of that. And then we have a postulate and two theorems that we're going to look at here. Alright, so the first one is the postulate, which is something that we just assume to be true. And so if we have two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. And so some of the formatting got lost here, but this is triangle TRS is similar to triangle PLM. And so what we have are the two angles in there, which means obviously that the third angle is going to have to be the same as well, because remember that the angles add up to 180. So these are going to match up. All the angles are congruent, and that's going to be enough to assume that they are similar. Again, it's a postulate, so we assume it to be true. So if we look down below, we have an example. And so we've given some perpendicularity statements. So these are perpendicular, which means they're 90-degree angles. And we're also given that they each have a 58-degree angle. And so we can explain why the triangles are similar. And the reason involves the postulate that we just talked about above. So we have two angles that are in common, which means that from the similarity postulate, the angle similarity, that the triangles are similar. And so the key thing here, this means therefore, triangle AMX is similar to triangle BKX. So here's B, right? That corresponds with A. X corresponds with itself, and M corresponds with K. So just like we had congruent statements where the pieces had to match up, we have the same thing for similarity statements. Here's our first theorem, the side angle side similarity theorem. This is similar to our side angle side congruence theorem. It's the same relationship of the side, the angle, and the side, except instead of the sides being congruent, the sides have to be proportional. And we'll look at what that means on the example right here. So we have by vertical angles, these angles here are congruent, so that's good. And we see we have the sides that include that angle, and if they're proportional, then this triangle is going to be similar. We can see just by looking at it, this is 3 times bigger, and then this is not 3 times, sorry, went the wrong way. The 12 matches up with the 24, and the 18 matches up with 36, which is 2 times bigger. So we'll see if we can get that. So we have that the angle is congruent because they're vertical. And then if I look at a proportion, right? If I look at 18 over 12, so if I took this side over that side, I want to make sure that I'm matching things up correctly, then I get 3/2. Now if I look at the bigger triangle, those are the pieces that match up. And how did I know that? I knew that I had a bigger side, and so I had to match up with the bigger side on the other piece. That's the easiest way I can talk about it. And so if I look at that ratio, again, a ratio is just a fraction, so I take this 36, I put it there, I take the 24 and I put it there, and I get, again, 3/2. So they are similar, right, because I have side, angle, side similarity. Now they're not congruent sides, but they're in this, they're proportional, right, they're equal ratios of 3/2, so they are similar triangles. I'm going to write my similarity statement. I have triangle ZVY is similar to triangle XVW by the theorem that's above. Alright? And then the last one at the bottom is side-side-side similarity. So if I have two triangles that are in proportion, all the sides, then I'm going to say that they're similar. Right? So if we go back, if we look back at this piece, we can see, right, that this is 3 times bigger, 3 times bigger, 3 times bigger, so they're going to be proportional if I was to work through them. Alright, so here's an example, and we need to talk for a second about a little bit of physics in terms of how they work. So, alright, and the physics thing, so we have a mirror from the base of a tree. Okay, here's my mirror. And one of the things, we're talking about light rays that are coming in, coming out. We're looking at the top of the tree. And then this is supposed to be like a pool table. One of the things that we're talking about is the angle that something comes in at is the angle that it reflects. The angle of incidence is the angle of reflection. And so these angles down here are going to be congruent. And that's going to help us a lot as we look through this. Because I notice I assume this is 90 degrees. That's 90 degrees. By the two angles that are congruent, these two triangles are similar by angle-angle similarity postulate. And that allows me to do a lot of things. Most importantly, set up a ratio. So, if I look back at this, right, I could solve for the height of the tree by, let's just call it x, setting up a ratio. And the easiest, I want to make it a little bit simpler for myself. So I'm going to take the x corresponds with that piece, and then on the bottom, the 24 corresponds with the 3. Because I'm not very sure of my ability to solve fractions, I'm going to set up a proportion where the x is on the top. I'm going to do x over 24. So I did purple over red, and you do that the same way on the other side, 5 over 3. And the reason that this helps me is now what I can do is to solve for x, I just multiply by 24. And I multiply by 24. Those go away, and x equals, well, 3 goes into 24 8 times, so it's 5 times 8, which is 40. So the tree is 40 feet tall, and that allows me to solve the problem. And again, down at the bottom we have some text around what it means for indirect measurement. We'll use it two ways, with a mirror or a shadow, and then you can look at some of the examples in the book, and we'll go over some more as well.